Now let's go into neural network architecture and boosting. Let's start with a visual of a two-layer neural network. And so here we start with our input layer. These are our x's. And here we would have some weights that we would apply to arrive at each of the nodes within the hidden layer. And then we have our output layer, which again, we will be using each of these nodes to then compile our final prediction within our output layer. Let's talk about how the weights are calculated. In order to know the appropriate amount to adjust our weights by, we need to know the derivative of the loss function with respect to the weights and biases. So what this means is we're looking at this loss function here. For example, the sum of squares could be used as the cost function. And what we're doing is we can then use backpropagation to find the weights. So this is going to involve a little bit of calculus. So let me just talk about through the visual here. So here we have a loss function, and that could be, for example, the sum of squared errors if we're looking at predicting a continuous variable. And then we have our weights that are being used for each of our readings, and then their nodes as we compile them. So during the forward propagation and the forward function for a layer, you need to know what that activation function in a layer will be. And then during the back propagation, the corresponding backward function also needs to know what the activation function for layer L is, since the gradient depends on it. And so what's going on here is we're looking at the gradient that's the derivative of the line, which, remember, the derivative is the instantaneous slope at a given point. And this is going to tell us that direction that we need to move toward at each point. If the value of a loss function is decreasing, that tells us it's good, and it would start adjusting the weights until that loss function continues to decrease, and it will reach a certain minimum. At that point, as they continue to adjust, we then start to increase. So that will stop at the green point and say, okay, this is actually the best point here. So the weights would be adjusted to the point at which corresponds to the lowest loss that you can have. It will continue to adjust up until it gets to that green point. So it had started off maybe off to the right, and it would continue down and then end back up at that green point. So if you want to learn more about the calculus behind the backpropagation, there is a video in the optional videos that you can watch, and we'll give you some insight into the mathematics and conceptual framework related to backpropagation. It's a completely optional video, but it would serve you well to have an understanding as to how these weights are being generated, and it just really serves as a brief introduction to that. Now let's look at the multi-layer perceptron. So this one includes 3 layers, which is the basic multi-layer perceptron neural network. First, we have an input layer containing a neuron or a unit for each input variable. The input layer neurons have no adjustable parameters or weights. And they just simply pass the positive or negative input to the next layer. Then we have a hidden layer with hidden units that by default perform a sigmoidal transformation of the weights, and the weighted and summed input activations. And then we have the output layer that shapes and combines the nonlinear hidden layer activation values. The number of parameters in multi-layer perceptron is going to continue to increase as we increase the k number of continuous inputs, as effectively as we increase the number of hidden layers. So the number of nodes and layers will increase the complexity of the model, and it will also result in the combinations increasing considerably. So for a linear perceptron, it will be equivalent to a generalized linear model. If G inverse is the identity link function, then this would be equivalent to the linear regression. But don't expect the results to agree exactly because of the different numerical algorithms that can be applied. But they are going to be very, very close to each other. So that is what the linear perceptron would look like. We have our x's in which doing a linear combination to arrive at our output. A multi-layer perceptron with 2 hidden layers is a little bit more complicated. And so you can start seeing here that we have our input layer, and now we have 2 hidden layers. This first hidden layer is then being passed onto the second hidden layer and then goes to our output layer. You can add as many layers as you would like to a neural network, but it has been noted that if you have only one input, so you only have one X, then there seems to be no advantage to using more than one hidden layer. But things get much more complicated when there are 2 or more inputs. when a second layer of hidden units is added, as we have done here, the second layer allows for different areas of the input space to be adjusted independently of each other. And so this gives a multi-layer perceptron with two hidden layers the ability to realize this continuous input mapping. So the gist of it is you are able to pick up higher levels of complexity within your relationships among variables. But unfortunately, the number of parameters and a two-layer network starts to grow pretty quickly. So one thing to note is that JMP is going to classify this layer that is closest to the input values as the second layer, and it is actually going to classify the layer closest to your output as the first layer. So just be aware of that. It's something to be cognizant of when you're seeing your labeling, that it would classify this as your first layer, which is the one that is closest to the output prediction, and then the one that's furthest, which is actually closest to your inputs, is classified as your second layer. Now let's talk about a different type of neural network called a skip layer perceptron. You still have a hidden layer, but now we have a skip layer that is added. So what that means is all the examples we have been doing so far, each of the inputs in this case look at our inputs and then they only go to the next layer. So here they go to, one hidden layer. But now with the skip layer, you can have it go all to the other hidden layer where you have as well as the output itself. So it can go to any layer within your model. And so you see here that X1 goes to the first node where W sub 01 and W0 sub 0n. And you can also have multiple nodes. It also goes to your output layer, which is the W0 sub 0 over here. So, which again, this is going to get us to our output prediction. So it can take you to any of the nodes. By adding direct connections from the input to the output layers, we can bypass our hidden layers as well. And it's possible to combine the linear and nonlinear network paradigms. And so this results again in what we call a skipped layer network. And because multi-layer perceptrons are already a universal approximator, in general, there's going to be little gain by adding these direct connections. However, a multi-layer perceptron is inherently stable. So this means that it will tend to perform poorly when applied to non-stationary data. So in this case, adding direct connections can help. So in other words, what is happening is that the system is changing over time, and this means that it is not stationary. And so we'll be talking much more about stationary and not stationary when we go into time series analysis. But if you have a series that is changing over time, which would indicate that it is not stationary, then a skip layer perceptron might help to model that type of behavior with us. So now let's talk about the Gaussian basis function. So here Gaussian basis functions use bell-shaped curves rather than the S-shaped curves of a sigmoidal basis function. And the Gaussian basis function is similar to a radial basis function. The Gaussian basis function is centered at 0, while the radial basis function is centered somewhere other than 0. That's the big difference. And the Gaussian basis function is seldomly used in the neural network because they take longer to calculate, which is going to slow down the training, and other activations perform just as well, sometimes even better. So in practice, you will not see the Gaussian activation function used very often. Now let's transition into talking about gradient boosting within the neural network. So boosting a neural network involves fitting a sequence of models where each successive model fits the scaled residuals to improve the overall fit. If the target is continuous, all of the things are done on a linear scale. If the target is categorical, all of the fitting is done on the logit scale. So this is similar to what we talked about with boosted trees, where effectively we are looking at the errors after each iteration, and we are considering those errors and how we are tuning our neural network. In this case, how we are tuning our weights. So that is effectively what gradient boosting would be doing from a mathematical perspective. And again, the takeaway is just that it's going to enable you to fit this sequence of models what each successive model it's going to take into consideration the scaled residuals to try and improve the overall fit. So now let's continue talking here about boosting networks and what's going on with them. So, what is a boosted network exactly? A boosted neural network is going to modify the response variable in a sense at each stage. A boosted neural network is the process of building a large additive neural network by creating a sequence of simple neural networks. And the base model should be 1 or 2 single layer models. You would not want to go beyond that. And so at each stage, the neural network is fit on the scaled residuals from the previous stage. And the magnitude of the scaling is controlled by the learning rate. The learning rate must be equal to a value between 0 and 1. Ranks less than or equal to 0.1 are going to be what are recommended in order to prevent overfitting a model. What parameters can you adjust to tune your model? Well, what we see is that there are several possible parameters that you can adjust to tune a neural network. So you can just adjust the number of hidden layers you have, the number of hidden nodes, the activation function that you use, the number of models that you incorporate, the learning rate, transforming the covariance. So you can log transform or take the square root or do some kind of data transformation. You can apply a robust fit. You can apply a penalty method, which is similar to what we talked about before with the lasso and ridge regression, where you can add a penalty to your cost function. You can adjust the number of tours or just how many iterations it kind of goes back in and redoes. So there are quite a few adjustments that you can make in a neural network. And as we see when we go into practicing and applying neural networks in our program. So what about the number of hidden units? How many should you include in your model? The optimal number of units required in each hidden layer is going to be problem specific. So there are general guidelines out there. One of them is from Principe et al., which says the number of units in the first hidden layer should be about twice the number of input dimensions. So 2 times the number of features you have. And then he has this other point, the number of units and the second hidden layer reflects the number of distinct regions needed, which is going to be very difficult to know beforehand. But as we will see, there are some ways you can determine the optimal number using empirical methods. And in this case, you can go through some iterations to try and find the most effective tuning pattern or parameter. And it can be very taxing for computers to do this because, as we discussed before, there are many different types of adjustments that you can make. But if you are looking at the number of hidden nodes, you can certainly just vary that. Now let's talk about some advantages of neural networks. So neural networks are flexible and can be used for both regression as well as classification type problems. And any data that can be made into a numeric value can be used in this model since neural networks are mathematical functions with approximation functions. Neural networks are good to model nonlinear data and with large number of inputs. So for example, if you're looking at images which have a lot of different inputs, it would be a really effective method for that. It's also a reliable approach involving many features. So if we have many features, it can be effective for that. It works well by splitting the classification into the layered network of simpler elements. So it is taking each of these nodes and layers and it is simplifying the problem and then going through this iterative successive process to try and find the hidden signal within your data. And then once trained, the predictions are pretty fast, but the actual compilation of the predictions themselves, the training, it can be pretty tedious and taxing on your computer as well. And neural networks can be trained with any number of inputs and layers. So JMP, we are limited to 2 layers, but again, in practice using other packages such as R and Python or others, you can go much deeper than that. And typically, when you're doing that, you get into the realm of what we call deep learning. And the thing is, the neural network works best with many, many data points, so you will need a lot of data points for you to do it and have it work effectively. especially if you want to go into that deep learning realm. You definitely need a lot more data points. So what are some disadvantages? So neural networks are black boxes, meaning you cannot know how much each independent variable is influencing your dependent variable. It's computationally very expensive and time consuming to train with traditional computers. So as I mentioned before, it'll be very taxing on your computer to do runs. The other disadvantage is that neural networks depend on a lot of training data. So this leads to the problem of overfitting and the lack of ability for generalization. So the model relies more on the training data and may be tuned to the data to the point where it doesn't generalize well, which is why we need to do validation to make sure that this doesn't happen.